Okay, let's continue with our topic of Thevenin and Norton. Just to do a brief recap, we introduced the concept of Thevenin and Norton theorems. These were postulated by a French telegraph engineer about 100 years, more than 100 years ago. Let's see. Section 3. All right. So as I was saying, this theorem was postulated by a French telegraph engineer more than 100 years ago. And a few decades later, an American engineer named Edward Norton also postulated his own theory based off of Thevenin's theorem. Both of these simply state that you could take a large linear network comprising of multiple sources, voltage and current sources, and multiple linear resistors, and you could represent them as a single voltage source or a single current source. Okay. If you remember the example, I stated that if your job was to find a value for R6, you could analyze the rest of the circuit by excluding R6 and determine that voltage source, the value of that voltage source and the resistance for that network, right? So this large linear network is equivalent to a single voltage source in series with a resistor, or it could also be considered as equivalent to a current source in parallel with a resistor. Okay. Both of these are very, very useful in electric circuit analysis. It's one of the most important theorems that we perform for higher level circuit analysis. Okay. The Thevenin network, and you will apply it to, I think in chapters 3 and 4, you'll encounter a situation where you apply a voltage or a current to a capacitor or an inductor, and you'd be tasked to find the actual voltage or current flowing through those components. So this is where you would apply Thevenin's theorem. So again, R6 is not part of your analysis, and we'd expect to find Thevenin voltage, Thevenin resistance, and Norton current. Okay. Now, the Thevenin equivalent circuit is representative of that large circuit, and so is the Norton circuit. So if A equals X and B also equals X, we can say A equals B, right? So we can also say these two circuits are equivalent to each other. Okay. A Thevenin representation of a circuit would be equivalent to the Norton representation of the same circuit. And taking it one step further, we can develop a concept known as source transformation, whereby you can transform a voltage source into a current source and vice versa, back and forth. That is also an analysis, not an analysis technique per se, but an application of the technique to simplify circuit analysis in certain cases. We will look at some examples at the end of this chapter. But for now, we'll stick a pin in source transformation and put it to the side. Okay. The main topic under consideration is to determine the Thevenin and Norton equivalent circuits. Okay. Now, when we say determine the Norton and Thevenin circuits, we are not learning anything. We are not learning a new analysis technique. Okay. You're learning something new. You're learning a new concept. You're learning a new theory, but it is not a new analysis technique. I want to establish that right off the bat. Okay. All the techniques that you have learned so far, those are the ones that you would apply to find these three quantities. So it's not a new analysis technique. So the most important part of learning something new in here is how to set up the problem. That is what you're learning. So the concept is new, and how you would set up the problem or how you would set up the circuit for analysis, that is the most important, because the analysis technique is not new. So first thing is, if the question states, determine the equivalent circuit between terminals A and B, or terminals X and Y. then you simply begin your analysis from those open terminals, right? You begin your analysis from those terminals. If the terminals of analysis are not given, and if the question states, find the Thevenin or Norton circuits as seen by a particular component, then you remove that component from your analysis. Case in point was this example where I said, if we wish to find a particular value for R6, we remove R6 from our analysis and we analyze the rest of the circuit without R6. Now, when you remove R6 from your analysis, it leaves behind open terminals. And you analyze the circuit between those open terminals. Does that make sense to everyone? Right? So that is the first and the most important step. Again, if the question states, determine it as seen by, and there are multiple ways to use that phrase. Sometimes that phrase is stated as seen by, or it might be stated that the component is a load resistance, or a load component. It would be your job to recognize what that problem statement is telling you. Okay, so sometimes this as seen by phrase can also be stated as a load resistor, load circuit, load component, or it would say a follow-on second circuit. Electrical engineering or electronic circuit, you always have multiple circuits connected in sequence. Okay, audio engineering, for example, you have a preamplifier at front, which is driving the amplifier circuit, which actually drives the speakers. So you have a preamplifier circuit, you have an amplifier circuit, then you have the final load, which is the speaker. But the amplifier circuit is the load for the first circuit. Does that make sense? So you have multiple stages. Sometimes you have multiple stages of amplifiers. So it happens all the time in electronic circuits. One circuit will drive the next, which will drive the next, and so on and so forth in a chain. So if it says as seen by, you remove that component, you remove that circuit from your analysis, and then you analyze between those open terminals. Now, you need to find three quantities, Thevenin voltage, current, and the resistance. So you analyze that circuit 3 times independently. Okay, you will redraw the circuit, and all 3 circuits would be different. All 3 circuits would be different. The circuit to determine Thevenin voltage is different from the circuit you would use to determine Norton current. And again, it will also be different from the circuit used to determine Thevenin resistance. Okay, all 3 circuits are independent of each other. They're all different circuits. So you have to perform 3 independent analyses. Okay, the results you obtain in one analysis has no bearing on the second one or the third one. All 3 of them are independent. If you have not yet looked at the final exam page, this is a 30-point problem in the final exam. Okay, it tests and assesses everything from chapters 1 and 2. It will test mesh current analysis, node voltage, REQ, voltage division, current division, determining the Thevenin and Norton. Runs over 4 pages long. Okay, it's multiple problems in one. Anyway, so again, analyze each circuit independently of the other 2. You can use any method you want. In the exam, I will state a particular method because I need to assess your understanding and knowledge of that particular method. Again, if you're doing homework or as a practicing engineer, you can choose any topic, any method you want. Node voltage, mesh current, superposition. You have done all 3 of these analysis techniques, right? So you choose any one of those, find the Thevenin voltage, find the Norton current, find the Thevenin resistance, your choice. When you have voltage, current, and resistance, the equation that relates the 3 is, of course, Ohm's law. So if you have the answers for any two of these quantities, you can find the third. So typically, some books or some professors would like to say, find the Thevenin voltage, find the Thevenin resistance, and then use Ohm's law to find the Norton current. I do not want students to do that. That is not the right way to learn. Okay. Obviously, if you have two of the quantities, you can find the third by using Ohm's law. But what if one of your quantities is incorrect? Let's say you find Thevenin voltage and you find Thevenin resistance, but your voltage value is incorrect. Then you end up with two incorrect values instead of just one. That's one thing. Second thing is, Thevenin resistance is sometimes the easiest to find. That's why some books and some instructors like to say, find the Thevenin resistance, find the voltage, and then calculate Norton current from Ohm's law. But all circuits are not reducible. You would not be able to find Thevenin resistance for some circuits. So at that time, you would find Thevenin voltage and Norton current, and then use Ohm's law to find Thevenin resistance. So there are certain cases where you would need to find Norton current separately. And that is the reason why I like to teach students, find all three quantities independently. You can also, your answers is also self-verifiable in that case. Okay. So again, do not use Ohm's law to find Norton current directly. You can use Ohm's law as part of your analysis, which is fine, but do not use it to find it directly. All right, three quantities, three independent circuit diagrams. First one is the voltage. Let's say you have a large circuit, doesn't matter what kind of circuit it is. I'm just gonna draw a large extended circuit. Okay, the example doesn't matter. That's why I went very crude, rudimentary drawing. If you had a component connected at those terminals, we remove those, keep the terminals open. I will say those are my terminals of analysis. You use any one of your three techniques to determine the open circuit voltage between A and B. Okay, you determine the open circuit voltage between the terminals A and B. That open circuit voltage is noted as VOC, and that is your Thevenin voltage for that circuit. That is the only modification you make. You do not have to make any other modification. You do not have to remove any sources. You do not have to open circuit or short circuit any sources. You simply determine where your terminals of analysis are. If it states A and B, you simply begin analysis as it is. If it states remove this component, if it states as seen by a component, then you remove that component and you analyze it between those open terminals. Once you have your voltage, that voltage is your Thevenin voltage. So VTH is the open circuit voltage VOC. All right, any questions? Again, this is the most important. Setting up the problem, these two slides are the most important. Okay. This is not a new analysis technique. It's a new theory. It's a new concept, but not a new technique. Then if you wish to find the Norton current, well, current needs a pathway to flow through. So you would place a wire between your terminals A and B. Basically, you're creating a short circuit between the two terminals. The current flowing from A to B, that is the assumed polarity. That is the assumed polarity at the beginning of your analysis. VOC has a plus up top, minus at the bottom, so current goes from A to B. That short circuit current flowing in that pathway is your Norton current, IN. Okay, that is your Norton current IN. And if you look carefully, the two circuits are different. Like the first circuit that you use to determine Thevenin voltage, all the components are exactly the same. Okay, the components are exactly the same, except the terminals where you're performing your measurement or you're performing your analysis. Those terminals are different. For Thevenin voltage, the terminals are open. For Norton current, the Thevenins are, for Norton current, the terminals are short-circuited. So you have to determine the current flowing from node A to B through that wire. Also note, because there is a wire between nodes A and B, it is the exact same node. Okay. Sometimes some circuits, when you have a wire in parallel with that resistor, if there's a resistor at the output end, it'll short circuit that resistor. And we will see that case in one of the examples. All right, any questions? Finally, we have the Thevenin and Norton resistance. This is nothing but finding Req. Req, which is something you did earlier in physics, which is something you also did earlier in this chapter 2. You take a large linear network of resistors, you have your open terminals of measurement, you find the total equivalent resistance between those terminals, and that Req is your Thevenin resistance RTH. But anytime you measure resistance, you have to disconnect all of the resistors from the power supply. All the energy sources in that circuit have to be removed from the circuit. So the way we do that is the technique we learned in superposition. You reduce all independent sources to zero, meaning you replace all voltage sources with a short circuit, and you replace all current sources with an open circuit. You redraw the circuit. The only thing that is left in that circuit are resistors. Once you have only resistors left in the circuit, find total Req. That is your Thevenin resistance. And that's why all three circuits are different. Circuit for Thevenin resistance does not have any sources in them. Otherwise, you cannot find the total Req. So again, Thevenin resistance, no sources. Norton current, you have a short at the output terminals. Thevenin voltage, open circuit terminals. Any questions? Think over that. Let me know if you have any questions. No questions? Yes. Yes. And we'll see that. So the question being asked was about Thevenin resistance. And so the answer would be on the next slide, which is we'll do the example. Actually, you will do the example and let me know what the answer is. So there are two more examples after this, but we'll only do this one for today. Okay. So it says determine Thevenin equivalent resistance between terminals A and B. The terminals are clearly stated. We do not have to do any modification to the circuit output terminals. Okay. A and B are right here. You simply think of it as simply connecting a multimeter at those terminals and trying to measure the total Req. If there was a resistor or component connected at A and B, the question might state as seen by R5 or R6 or something else. Okay, then you would remove that component from your analysis and analyze the rest of the circuit. But A and B, we need to find Req between A and B. So let's start with removing all the sources. What happens to the voltage sources? We place a wire and current sources, open circuit, remove it, right? So go ahead and draw it out. There are 4 resistors in the circuit between A and B. You have 2 current sources and 3 voltage sources. Go ahead and finish redrawing the circuit, and then I will draw it out on the screen here. And then you can also go ahead and determine your REQ. Remember, if you're trying to find REQ, you start at the farthest end and you move towards your terminals of measurement one step at a time. Any questions? Anyone? I'm going to draw out the spaces where the current sources and the voltage sources were connected, just to illustrate. But there's actually no need to actually make the wire, draw out the wires at all. Okay, you can leave the spot empty. So what do we see? You start at the farthest end. You have R1 in parallel with R2. Right, R1 parallel with R2, which would be in series with R3, which would then be in parallel with R4. You'll have the same answer. Right. Now again, this and most of the circuits that you see would be reducible, right? So you can easily do this. But if it was not, then you would need to find Thevenin voltage and Norton current and apply Ohm's law to find RTH. Okay. All right, we'll end class here today, and I will continue with the 2 examples on Wednesday. If you have any questions, let me know. Stop by my office hours, student hours, this afternoon.